Today's lesson is on scientific notation. A scientific notation is a number when it is expressed in the form a times x to the n, where a is going to be a number between 1 and 10, and n is going to be an integer. Examples of scientific notation would be 5.43 times 10 to the 6. Notice that 6 is an integer and 5.43 is somewhere between 1 and 10. Okay, we can't have it any bigger than 10, otherwise we can always add another exponent to the times 10 to the exponent. 9.278 times 10 to the negative 3. Negative 3 is still an integer, and 9.278 is between 1 and 10. So these are both good examples of scientific notation. Here are some that are not good examples of scientific notation. 51.43 times 10 to the 6 is not, because 51 is too big. I could rewrite this as 5.143 because this is too big, times 10 to the 7. This would be correct, but the second one with 51 would not be correct. And then our last non-example would be 9.278 times 10 to the 9.1. 9.1, that's not okay because it's not an integer, meaning a positive or negative whole number. So this is not examples. So let's just look about what these scientific notation means. 5.43 times 10 to the 1, if we get our calculator out, 5.43, that's going to turn out to be 54.3 when you multiply by 10. When you multiply 5.43 times 10 squared, what is 10 squared? 10 squared is 100. So when I multiply that gets you 543. All right, how about 5.43 times 10 to the 3? 10 to the 3, that's 1,000, because 10 times 10 times 10. So this turns out to be 5,430. Okay, well, what happens if you go with negatives? 5.43 times 10 to the negative 1, that is kind of like dividing by 10. So it's like 5.43 divided by 10. Because what is that 10 to the negative 1? That means move it to the denominator, right? So this turns out to be 0.543. Well, what about if you times 10 to the negative 2? Well, times 10 to the negative 2 is kind of like divide by 100, because the negative says go down to the denominator, which means it's to divide instead of a multiply. 10 squared is 100, so this turns out to be 0.0543. Remember, when dividing by powers of 10 is actually really easy. So when we divide by 10 to the 3, that's like 1,000. So this turns out to be 0.00543. So if we look at these examples, it turns out that if the exponent on the 10 is positive, like the numbers on the left column, all you're going to do is move the decimal over to the right the same number of places as the exponent in the number. If the exponent on the 10 is negative, like the examples in red on the right, then you're going to move the decimal over to the left, the same number of places as the exponent. So let's show how to change these that are examples that are in scientific notation to regular standard numbers. So if I have the exponent here as positive, then that means I'm going to take this 8.8 and move the decimal over to the right 6 places. 1, 2, 3, 4, 5, 6, and fill all those places with zeros. So that gets me 8,800,000. So 8.8 times 10 to the 6 really is 8,800,000. We know it's getting bigger when the exponent is positive. That means you're getting a big number. Big numbers mean you move it to the right. Our next example has a negative exponent. Negative exponent means you have a really small number, so you're going to move it actually to the left, not the right. So we're going to take 7.8 and we're going to move this decimal 1, 2, 3, 4, 5 places. which leaves us with 0.4078. That's a really small number. But if you ever have a negative in the exponent, that means you're dividing, which means it's going to be a really, really small number. And our last one, 4, is a positive number, which means we're going to get a big number and move our decimal to the right. So we have 4.563 times 10 to the 4. So I'm going to take that decimal and move it over 4 places to the right to get 45,630. And that's how you change scientific numbers to standard numbers. Next, we're going to do the opposite. We're going to change standard numbers to scientific notation. So the first thing you want to do is identify the first non-zero digit. Notice we have lots and lots of zeros, so we're looking for this first non-zero digit. In our first example, that's the 9. Count the number of places the decimal needs to move to be directly behind the first non-zero digit. The number will be the exponent on the 10. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have to move this 9 places. So we have 9, and we'll move the decimal there, 0.876 times 10. We moved it over 9 places, so the exponent is going to be 9. Now, if the standard numbers absolute value was very large, so 9, I think that's 9 trillion, is really, really, really large, so the exponent should be positive, okay? That's what step 3 is saying. Now, if the standard numbers absolute value is very, very small, like 0.00000, then the exponent will be negative, okay? So let's do the next example. I want my new decimal to be right between the 5 and the 6 because 5 is, step 1 is the first non-zero digit. So my decimal place is already written here, so I'm going to move it over 1, 2, 3, 4, 5, 6, 7 places. That leaves me with 5.68 times 10 to the, and now is it positive 7 or negative 7? In this case, it's negative. Why? Because this is a really, really, really small number, whereas the one before it was a really, really, really big number, so the exponent is positive. Big numbers mean positive. Very small numbers is going to get you a negative exponent. Small meaning like 0.000 something small. Okay, so our next example, negative 34 million, is a big number. Now I know it's negative, but we're not caring about the positive or negative. It's a really big number. So because this is a large value, that means my exponent will be positive. Now, the negative is just going to stay with the whole number. So my decimal is right there at the end of all those zeros, and I want to move my decimal to between the 3 and the 4 because 3 is our first non-zero digit. So I'm going to count how many decimal places it needs to move. 1, 2, 3, 4, 5, 6, 7. So we have negative 3.4. Notice the negative just stays, okay? Times 10 to the, I counted 7 places, and because it's a big number, it's going to be a positive 7. Negative 0.0324, that's a small number. Now I'm not talking about the negative part, I'm just talking about the 0.0 part. It's pretty small, so that means my exponent is going to be negative. I want my decimal to be between the 3 and the 2 because 3 is the first non-zero digit. I'm going to move the place over 2 places, so that's going to be negative 3.24. Notice the negative just stayed on the number in front. I moved the decimal over 2 places, and because the original number is very small, I'm going to have a negative in the exponent. So our next steps are to try to figure out how to multiply scientific numbers. So to multiply scientific numbers and keep them in scientific notation, you're going to simply multiply the number in front. So 2 times 4 is 8 times 10 to the, well, we have 8 up in the exponent, we have a 5 in the exponent. We have the two bases that are the same. Notice this base 10 and this base 10 are the same. And what we learned from integer exponents is if the bases are the same, what are you going to do with the exponents when you multiply? Well, you add. You add the exponents. So it's simply 8 times 10 to the 13, and that's it. Notice that 8 is still between 1 and 10, so we don't have to manipulate that anymore. That is just completely done. Our next problem, we have 8 times 10 to the 5 times 3 times 10 to the 3. So 8 times 3 is 24 times 10 to the, I'm going to add my exponents. I have a 5 and a 3, and that adds up to 8. But unfortunately, this isn't done. And the reason it's not done is because 24 is too big. Our number out in front, to be in scientific notation, has to be between 1 and 10. So what I'm going to do is I'm going to take this decimal and move it over one place to make that 2.4 times 10. And because I moved it one place to the right, I'm going to add one more in the exponent and get 9. 2.4 times 10 to the 9 is the same thing as 24 times 10 to the 8, but the one written in blue, 2.4 times 10 to the 9, is in scientific notation, where the one in red is not in scientific notation because 24 is too big. And then the last type of example is dividing scientific notation. So again, 9 divided by 3 is going to get me 3 times 10 to the, when we divide exponents, notice the bases are the same, so it stays the same 10. What do you do with the 6 and the 3? Well, when you're dividing, let's pretend you had 6 tens being multiplied on top and 3 tens being multiplied on the bottom. After you cancel out, how many tens do you have? 3. The quotient rule says to subtract. And because 3 is between 1 and 10, you are still within scientific notation. And our last example, we have 8 divided by negative 4, that's negative 2, times 10 to the negative 3 over 10 to the negative 1. Negatives. We don't like dealing with negatives, do we? So let's see. Let's change this. 10 to the negative 3, we're going to move downstairs to be 10 to the positive 3. 10 to the negative 1, we're going to move upstairs to make that 10 to the positive 1 now. After we divide, we get 10 to the 2 in the denominator. So we have negative 2 times 1 over 10 to the 2. Now in scientific notation, we are allowed to have negative exponents. In fact, we have to have negative exponents. We're not allowed to have 1 over 10. It has to be some number times 10 to the exponent. So if I take this, remember our tenant from downstairs, he's not really happy where he's living downstairs, but we have to move everyone upstairs. Everyone has to be upstairs. So if I move him upstairs, it becomes negative 2. And this is our final answer for that division problem in scientific notation. And this concludes our lesson on scientific notation.